Hello students, welcome to the amazing platform of Physics Wallah. Welcome to the PW English channel, my dear students. We have completed two lectures basically of chemical kinetics, and we have studied a bit few topics in these two lectures. We actually understood how to write a rate law, what is order and molecularity, and in the last lecture we actually studied everything about a zeroth order reaction. If you are clear with the zeroth order reaction, you will definitely be clear with the first order reaction, because the method, the steps to find out the integrated rate law is exactly same. Okay, so my dear students, the second lecture is of utmost importance, because you will clearly understand what is the basis of zeroth order, and only then you will be able to understand the first law. I hope you are thorough with the first lecture and the second lecture. Now let's start our first order reactions. Okay, so what are we going to discuss today? We'll be discussing about the first order reaction, and then we'll be practicing a lot of questions. So let's start this amazing session today. Let's talk about the first order reaction. So my dear students, when we talk about the first order reaction, I told you it is exactly like we calculated for zeroth order. So first, let's assume a reaction we have from A to B. Let's say it is a first order reaction. Let's say it is a first order reaction. If it is a first order reaction, then according to the rate law, we can say that R is directly proportional to the reactant's concentration raised to the power n. Now, since it is a first order reaction, so the order of the reaction is 1. So this means that your rate is directly proportional to A raised to the power 1. R will be equal to K A raised to the power 1, right? Yes, perfect, my dear students. So this is something which you need to understand. We have calculated this. Okay, so now I will just let you know how you can calculate the units of the rate constant here. This is the rate law expression for a first order reaction. Okay, now let's write the unit of rate constant K. See, if you see, you can say that K is actually equal to rate upon the concentration of the reactant raised to the power 1, right? Yes, this is clear to you. You know that what is the unit of rate? It is mole per liter per second. Okay, yes. So the unit of rate is mole per liter per second divided by, let's talk about the concentration unit. My dear students, concentration is always your molarity, and unit of molarity is mole liter inverse. So this will be mole liter inverse. If we talk about the units, we can see that mole will be cancelled by mole and liter inverse will be cancelled by liter inverse. So the unit of K that came out is equal to the second inverse. This is the unit that we calculated from the rate law we just derived, right? Yes. Now, my dear students, I just want to cross check whether my answer is correct or not. And how can I cross check whether my answer is correct or not? We can cross check it by finding out the unit of rate constant by the general formula we actually calculated in the first lecture, right? Yes. So let's try to cross check our answer. So the general expression of rate constant K was mole 1 minus n liter n minus 1 second inverse, right? Yes, where n was actually the order of the reaction, Now, since, my dear students, your order of the reaction is 1, so n value will be equal to 1. Yes, so n is equal to 1. Let's just put it mole 1 minus 1 liter 1 minus 1 second inverse. So the unit came out to be second inverse, and also the unit from our rate law also came out to be second inverse. So what can we say? That yes, they both match, which means that it is absolutely correct. Okay, perfect, my dear students. So this is how we cross check whether the rate law we have calculated is correct or not. Okay, perfect, my dear students. So this is the was the first part that we calculated for zeroth order also, and we have calculated for the first order also. So please write it, and then we'll move forward. Okay, I hope you've written it. This was the first order starting part. Now let's talk about the integrated rate law, because for a first order reaction we need a integrated rate law. And let me tell you, the first order reaction is actually the most important part of this chapter. The most of the questions asked are from this particular part. So you need to be clear with all the expressions we'll be calculating in the integrated rate law. So let's write the expression. First, write the heading, my dear students. Integrated rate law. Okay, so this is the integrated rate law. For this, we need the reaction. So let's write the reaction first. The reaction is from A to B. Okay, so ma'am, this is the first order reaction. So first and the most important thing that we will be doing is we'll be writing the instantaneous rate. Okay, how to calculate the instantaneous rate? I hope all of you remember. If you don't remember, then I am sorry, you need to revise your first lecture. Instantaneous rate. So my dear students, for instantaneous rate, we used to write R is equal to minus D concentration of A by dt. This was your instantaneous rate, right? Yes, this was how we used to calculate the instantaneous rate. Perfect. Now, my dear students, we'll be applying the rate law. Let's apply the rate law. If we will apply the rate law, what will we do? We'll say that, ma'am, R will be directly proportional to the reactant's concentration raised to the power order, right? Yes, and the order of the reaction is 1. So the value of n is 1. So R is directly proportional to A raised to the power 1. Let's remove the proportionality. R will be equal to Ka. I hope it is clear to you. Yes. So now this was your first expression and this is your expression for rate from the rate law. So now we have two different expressions. The first expression is for the instantaneous rate, right? Yes. And the second expression is for the rate is from the rate law, that is R is equal to Ka. Right? Yes. So these two are the rate expressions. Now we calculated from any formula. We know that as long as it is the rate of the same reaction, they both should be equal. Right? Yes. So ma'am, obviously this rate and this rate, that is the 1 and 2 expressions, both should be equal because they are the rate of the same equation. Right? Yes. So I'll say that 1 will be equal to 2. If 1 is equal to 2, this means that minus dA by dt is equal to Ka raised to the power 1. Right? Yes, this is the expression. We equated both the rates. Now, my dear students, what are we going to do? We'll be integrating on both sides. We'll be integrating on both sides. Before that, what you will do, you just cross multiply it, write minus of dA by A equal to K dt. Okay. Let's put this negative sign here. So this would be dA by A is equal to minus K dt. Now let's integrate on both sides. Okay. So integrating on both sides. This would be dA by A is equal to minus integration of minus K dt. Whenever you integrate, you need to put the limits. Whenever you integrate, my dear students, you need to put the limits. So this would be from A0 to AT. And this would be from 0 to t. Now we need to understand what is A0, what is AT, right? Yes, all of you remember, but still I'll have to write it. A0 is the initial concentration of reactant at time t. Okay, and if you talk about AT, it would be the concentration at time t is equal to 0. Right? Yes. Let's talk about AT. What is AT? AT will be the concentration of the reactant at time t. So, concentration of reactant at time t. Okay. Yes. So this is the expression. This is the main important thing that we needed to understand. We have put the limits here. We have integrated. Now, my dear students, since k is a constant, so it will not get be integrated. So we'll write integration. Okay. Integration of dA by a will be equal to minus k dt. The limits would be from a naught to at and from 0 to t. So now, my dear students, we'll be using a few of the log properties. So I'll just make you understand what log properties are we going to use. Okay, so the log properties which we'll be using is, my dear students, I'll write it here, using integration of dx is always equal to x. Okay, and the other property we'll be using, integration of dx upon x is equal to natural log of x. Okay, these are the two major integrating formulas we'll be using, that whenever you integrate dx you get x, whenever you integrate dx by x you get natural log of x. Now let's try to incorporate these in the expression. Okay, so now we are integrating dA by A. If we are integrating dA by A, can I use this one expression? Yes, this will be equal to natural log of A, and the limit would be from A naught to A t. This will be equal to minus k into integration of dt. Integration of dx gives you x, so integration of t would give you dt will give you t. So now, and the limits would be from 0 to t. Now, when you write this, now you need to understand that whenever you put the limits, always the upper limit is to be added first and then subtracted by the, and then the second unit we put the second unit and we subtract it. Okay, so this would be, my dear students, ln of at minus ln of a naught is equal to minus k t minus 0. Okay, what did I do? I integrated it. The upper limit ln of at minus ln of a naught is equal to minus k t minus 0, which is k t. Okay, yes, perfect. I hope you're clear with this. Now, my dear students, I'll make you understand that we'll be using one more log expression, and what that expression is, I'll tell you again. Now we will be using, whenever you have log of x minus natural log of y, this is actually equal to ln of x upon y. Or if you say ln of x plus ln of y, this means that ln of x into y. These are the two log properties which we will be using right now. Whenever you have ln of x upon y, you can write it as ln of x minus ln of y, and vice versa. Whenever you have ln of x plus ln of y, you can write it as ln of x into y, and vice versa. So we'll be using this expression in the R derivation. See, now you have ln of at minus ln of a naught. So we'll be using this expression, and we can write it as ln of at upon ln of a naught is equal to minus k t. Okay, perfect. I hope you're clear with this. So my dear students, this is an important expression. This is an important expression which you can use in your numericals, Okay. Okay, now what we will do, we'll use this negative sign this side. We can use negative this or this, right? Yes, so we can say that ln of, I'll say minus ln of a t upon ln of a naught is equal to kt. We can write this as like this. Yes, now we'll be using one more log expression. I'll tell you again which expression. So now, using, my dear students, whenever you have ln minus ln of x, you can say that this is actually equal to ln of x raised to the power minus 1. So this minus 1 comes to the power of x, and then this is whole power negative, so this is actually equal to ln of 1 upon x. So now we'll be using this log property. Now we'll be using this log property. Okay, I'll make you revise everything, don't worry, but for now, just try to understand each and every step. Okay, so if I am using this in this particular expression, can I say that ln of 80 upon a naught whole power negative is equal to kt? Can I say that? Yes, ma'am, you can say. And since it is whole power negative, so the both of them will get reciprocated. So ln will be equal to a naught upon a t. And this will be equal to k t. This is yet another expression which is of utmost importance. It is yet another expression which is of utmost importance. So you will be using this. So you need to memorize this expression. Okay. Yes. So we derived this expression. And this expression is very important. We use it in numericals. Now what are we going to do? We'll just solve it further, my dear students. Just see how are we going to solve it. Let's use this expression ln of a naught upon at is equal to kt, right? Yes. So what are you going to do, my dear? No. Yes. Now you can say that k is actually equal to 1 upon t. I just cross multiplied it, ln of a naught upon a t, right? Yes. Yet another expression which will be widely used in the calculations. And this is your integrated rate law for the first order reaction. So if you want to write it, you can write it that this is the integrated rate law for first order. This is your integrated rate law for the first order. Okay, what is it? K is equal to 1 upon t ln of a naught upon at, where a naught is the initial concentration and at is the concentration of the reactant at time t. Okay, I hope you're clear with this. Perfect, my dear students. Now let's just try to, this is your final expression. You only need to understand this. Now we'll be finding out few more things from this expression. Okay, so now we will be using something, my dear students, said as using, whenever you convert natural log into log base 10, you multiply it by 2.303, then it comes to be log base 10x. So if you want to convert any natural log to log base 10, you just multiply it by 2.303. So now we will be writing this expression as k is equal to 1 upon t. Natural log will be equal to, can I say it as 2.303 upon t? Log base 10 a naught upon a t. Right? Yes. This is the another expression which is used in calculations. This is the another expression which is generally used in your calculations. You just converted the natural log to log base 10. Okay, perfect. I hope you're clear till now. I hope you don't have any issue till now. Perfect, my dear students. These are the few things which you need to understand. Okay. So should I make you understand the whole the derivation? Let's revise it. Let's try to revise it, and at the same time you'll just pause the video and try the question yourself. Okay. So see, what we did, we considered a reaction A to B. And then we first wrote its instantaneous rate and then we wrote its rate law. Now we equated both of them because they were the same reactions rate. When you equated it, you will just integrate it like we did in the zeroth order reaction. When you integrated it, you had some different expressions. So I told you that the integration of dx is always x and the integration of dx by x is ln of x. So this is dA by A. So this would be ln of A, limits a naught to at, and that is dt. So the integration of dt would be t. So the integration of dt would be t and this would be from 0 to t. I put the limits ln of at minus ln of a naught is equal to minus kt. I told you that now we'll be using a property of log, which is whenever you write ln of x minus ln of y, actually that is ln of x upon y. And this is ln of x plus y, ln of xy. We'll be using this expression. So since it was negative, so we did use it expression and we found a relation. Now we incorporated this negative here, and I told you that whenever minus of ln x is written, it means that ln of x raised to the power minus 1, which can be written as 1 upon x. So we used this expression in this. This was whole power negative, so obviously this will be reciprocated, and this is the final expression that came out. Okay, now next, this was your integrated rate law, an important expression. Then my dear students, ln of a naught upon at is equal to kt. So this means that k is equal to 1 upon t, ln of a naught upon at. This was the integrated rate law for the first order reaction, and if you want to convert it into the log base 10, you will have to multiply it by 2.303. So this is the expression that we found out. Okay, I hope you've paused the video at the times and you've written this particular part. Clear? I hope you don't have any issues till now. Yes, perfect, my dear students. Now what are we going to do further? Let's just see. Okay, beta. So now what are we going to do is that we have written this now. Consider my dear students, you have a reaction. I hope you might have studied this part in your chemical equilibrium chapter. If not, then don't worry, I am here. You have a reaction from A to B. Let's say initially at time is equal to 0, you had A amount of your reactant. So what is A? Amount of reactant. Initial amount of reactant. So can I say that actually A naught is equal to A? Right? Yes. Now, no product was formed at time 0. No reaction took place. After some t is equal to t time, let's say some reaction took place and X amount of your reactant is consumed. So what is X? Amount of reactant consumed. So if X amount of reactant is consumed, this means that A minus X amount of your reactant might have left. So can I say that A T is actually equal to A minus X, and this is the amount of reactant left. This is the amount of reactant left, right? Yes. So ma'am, this would be A minus X, and X amount of your product might have formed, right? Yes. So if something like this is given to you and you have to write the integrated rate law, so you have to just remember the first integrated rate law, K is equal to 2.303 upon T log base 10 A naught upon A T. Can I just write this expression as K is equal to 2.303 upon T log, what is A naught equal to A upon what is AT equal to A minus X? Yes, we can say. And this is your expression for the integrated rate law. So this is the expression for integrated rate law. Right? Yes. So these are the variations of the integrated rate law. The basic idea is exactly the same. So you can also see this kind of expression somewhere. So just don't get confused. Okay. I hope you're clear with this. Perfect, my dear students. Pause the video, write it, and then we'll move forward. I hope you've written it. Perfect, my dear students. Now we'll be understanding a few more things. A few more things, what I mean is, you might have heard of something called as degree of ionization. You might have heard about something known as degree of ionization. So now, my dear students, we'll be writing the integrated rate law in terms of degree of ionization. Okay, so this is something which you need to understand, that integrated rate law in terms of degree of ionization. Degree of ionization is denoted by alpha. Okay. This is something which we study in the equilibrium chapter when you talk about the electrolytes and their degree of ionizations. Okay. So now let me tell you what is degree of ionization. Alpha is actually amount reacted upon total amount. It is the amount reacted upon total amount. Okay, perfect. I hope you're clear with this. Now, the reaction which we wrote initially from A to B. Initially, my dear students, at t is equal to 0, you had A amount of this and you didn't have any of the product. At t is equal to t time, A minus X, where X was the amount reacted and X was the amount of the product formed, and A minus X was the amount that is left. Okay, so now if I ask you what will be the value of degree of ionization here, what will you say? The amount reacted, how much amount is reacted? X amount is reacted. And what was the total amount? A was the total amount. So can I say that X is actually equal to A alpha? Can I say that X is actually equal to A alpha? Yes, I hope you're clear with this. Yes, ma'am. Perfect. So now, my dear students, the expression we just derived, K was equal to 2.303 upon T log A upon A minus X. I hope all of you remember this expression. Now, in this expression, we just derived the value of X, which is A alpha in terms of degree of ionization. Just incorporated into this expression. This will be equal to K is equal to 2.303 upon T log of A upon A minus A alpha. Let's take A common. My dear students. Then your K will be equal to 2.303 upon T log A upon A into 1 minus alpha. A cancelled. So your K will be equal to 2.303 upon T log of 1 upon 1 minus alpha. And this is your expression, your integrated rate law in terms of degree of ionization. And whenever you are given degree of ionization, you need not calculate what is the initial amount, how much is reacted. You don't care, because you are actually given the alpha value. Just incorporate it into this expression and you will find your answer. This is the beauty of chemistry, that whenever you are given degree of ionization, you only need alpha value. You don't need the initial amount A or how much amount is reacted X. No, you only need this expression. Okay, I hope you're clear with this. So this is something you need to memorize again, my dear students. So these are the expressions which I have made boxes. These are the expressions which will be used in the numericals. Okay, so try to understand each and every part very seriously. So if you want to write it, you can just write it. Integrated rate law in terms of degree of ionization. Alpha is the amount reacted upon the total amount. Amount reacted is X and the total amount is A. So the value of X came out to be A alpha. So this was the expression we derived. We put the value of X in this and we finally come to our important expression, which is 2.303 upon T log 1 upon 1 minus alpha. Okay, yes, perfect, my dear students. So this was all about the first law's integrated rate law for the first law. Okay, I'm sorry, integrated rate law for the first order. Okay, yes, I hope you're clear with this. Okay, my dear students, let's move forward. Now, there are a lot of numeric graphs asked to you relating to this. So let's try to derive some graphs. Okay, so our next heading would be graphs. Try to understand each and every graph, because most of the questions that are asked from the graph. So my dear students, the first graph that is asked is rate versus concentration. So the graph between rate versus concentration for a first order reaction, how are you going to derive? It is the first thing that you write for the first order reaction, that R is equal to K A raised to the power 1. So can I say that actually your rate is directly proportional to the concentration of reactant? So your plot will be something like this, where this is your rate, this is the concentration of the reactant, and it will be a straight line graph. And this means that whenever the concentration decreases, see here, if it is rate 1 and this is rate 1. This would be rate 1, right? Let's say this is A2. This would be rate 2. As your concentration of reactant is decreasing, your rate of reaction is also decreasing, right? Yes. So we can say that the rate is directly proportional to the concentration of the reactant, right? Yes. Perfect, my dear students. You can pause the video, write this graph, because you will be asked questions related to graph a lot of times. Okay. I am feeling a little cold. Just a second. Yes, perfect, my dear students. I hope you're clear till now. Rate versus the concentration, right? This is the first graph that is generally asked. Till now, everything is clear. Next graph that is generally asked to you is concentration of reactant versus time. Okay, so now let's try to understand how will we derive this particular part. For this part, my dear students, you need to go to the integrated rate law part, and I'll tell you where. Just a second. The first expression that I made you make a square, this expression, ln of AT upon A naught is equal to minus KT. Just memorize it. Ln of AT upon A naught is equal to minus KT. So ln of A naught AT upon A naught is equal to minus KT. This was the expression. This was the expression. Okay, my dear students? Yes. So now what are you actually going to do is, you'll actually here, my dear students, use a log property. I am sorry, but one more log property you will have to understand. And what is that log property? I'll tell you. What are we using? Using, my dear students, ln of x is equal to, let's say, y. Whenever ln of x is equal to y, then you can say that x is actually equal to e raised to the power y. Whenever you have ln of x equal to y, you can say that x is actually equal to e raised to the power y. Okay, perfect. So now use this into this. So can I say that a of t upon a naught is actually equal to e raised to the power minus kt? Because here my x is at upon a naught. X is at upon a naught, and y is equal to minus kt. I hope you're clear with this. Yes. So from this, we can say that at is equal to a naught e raised to the power minus kt, right? S. And you have to find out the graph between concentration of reactant. So this is the concentration of reactant that is changing, because initial concentration is a constant. So we don't need that. We need the concentration that is continuously changing versus time. And if we see that, we can say that it is exponential raised to the power minus of kt. This means that, my dear students, your plot of concentration of reactant versus time will be AT versus time. This will be exponentially decreasing. This will keep on exponentially decreasing, my dear students. This is very important to understand, that the concentration is decreasing exponentially with time in the first order reaction. And this plot is asked by in the question papers by the examiner a lot of times. So you need to understand this plot, and you need to understand how this particular plot came out. Okay, so I hope you're clear with this. Just pause the video. You can write this, because this is very, very important. Perfect, my dear students. Till now, everything is clear. Okay. Now let's try to understand a bit more. Okay. So the expression which we calculated in the starting part, which was, let's talk about the expression ln of a naught upon at. Okay. let me make a line here. Ln of A naught upon AT is actually equal to, I think this was equal to minus KT. No, just a second. The expression which we calculated in the starting, this expression, which I told you that increasing this, expanding this will give you the first integrated rate law. This is ln of A naught upon AT is equal to KT, right? Yes. So ln of A naught upon AT is equal to KT. This is the first expression which we derived, and from here we calculated all our integrated rate laws. So what you have to do is, you know what are we going to use? Using, my dear students, ln of x upon y is equal to ln of x minus ln of y. So we'll be using this expression in this. Okay, so let's try to incorporate this. This would be, my dear students, ln of A naught minus ln of AT is equal to KT. Okay, yes. Now I want to convert ln natural log to 2.303 part, right? Yes, that is log base 10. So let's convert it. We know that ln of x is equal to 2.303 log base 10 of x. So let's use this expression. This would be 2.303 log A naught minus 2.303 log AT is equal to KT, right? Yes. Let's just divide the complete equation by 2.303. Divide by 2.303. This will give you log of A naught minus log of AT as KT by 2.30. Right? Yes, I hope you're clear till now. I hope you don't have any issues. Now, just take this negative sign there and bring KT upon 2.303 this side. Okay, so what will happen? Can I say that log of A naught AT is equal to log of A naught minus KT upon 2.303, right? Yes. Now we'll be using this expression. Where are we going to use? I'll just make you understand. You are generally asked to plot a graph between log of AT versus T. If you are ever asked to plot a graph between the concentration of your reactant and time, the plot will always be, my dear students, just compare it with y is equal to C plus mx. Can I say that your y-axis is log of AT, your x-axis is time, and your intercept, which is C, is equal to log A naught, and your slope, which is equal to m, which is given by tan theta, is actually equal to minus k upon 2.303, right? Yes. Now let's try to plot the graph. You have log of AT and you have T. It is a straight line graph with a negative slope. So the graph would be something like this. And your intercept here would be log A naught. And your slope would be minus k upon 2.303. So these are the few graphs that are asked to you, and you have to find the expression on your own. I have tried to make you write all the graphs right now, but there are a few graphs which you might have been asked out of the blue in the exam paper. But if you know the expressions, you will definitely be able to draw the graphs. Okay, yes. So this is yet another graph where you will be using this expression the first expression that we used to calculate the integrated rate law, and then you'll use the log property here and incorporate it into the straight line equation and compare it with this, and this is the final graph that you'll come out with. Okay, so please pause the video, write it, and then we'll move forward. Okay. I hope we have done everything about first order now. We have calculated the integrated rate law. We have tried to make the graphs of all the possible things that we could be asked. Still, if something is left, we'll cover that as well. Now let's move forward. Here you have, in first order reaction, the rate decreases linearly with concentration. I hope now you can say that your graph between rate and time would be a linearly decreasing graph, and this is something like this we made in the first graph. This was the graph, right? Yes, perfect. And this was derived from rate is equal to Ka. Oh, sorry, this would be concentration, na? Yes, okay, perfect. Let's move forward. Second, therefore, the concentration decreases exponentially with time. I hope you're clear with this. We just drew our expression where we said concentration is decreasing with time, where your AT was actually equal to A naught e raised to the power minus K T. This was the expression we found out, and this was the graph which we drew, right? See, my dear students, the next thing which you need to understand is, therefore, the reaction would never be 100% completed. Why the first order reaction is never 100% completed? Because when you extrapolate this graph, when you try this graph to extrapolate, you will see that at one particular point, it will be parallel to the x-axis. And that is, it is getting parallel to the time. It will never be, you'll never get a time where the concentration cuts the x-axis, and that is the reason it will never be equal to 0. It will never be equal to 0. So this is the reason why the reaction is never ever 100% completed. The reaction is never ever 100% completed. Okay? I hope you're clear with this, my dear students. Okay, let's move forward. Now we'll be calculating the half-life of the first order reaction. I hope all of you remember what is half-life. Half-life is the time period where the half amount of your initial concentration of the reactant is left, right? Yes. So can I say that at T is equal to T half, the concentration of the reactant AT becomes A naught by 2. I can say that. Can I say that? Yes, ma'am, you can say that. Okay. So now we'll be using the integrated rate law of the first order reaction exactly like we used in the zero order. So integrated rate law for first order. So integrated rate law for first order tells you that K is equal to 1 upon T ln A naught upon A T, right? Yes. So let's just cross multiply it. We need T is equal to 1 upon K ln A naught upon A T. Now T is equal to T half and AT is equal to A naught by 2. Right? Yes. Let's just put it into the expression. You will get T half is equal to 1 upon K ln of A naught upon A naught by 2. Right? Yes. So A naught will be cancelled. So T half will be equal to ln of 2 by K. And this is the expression for your half-life for first order. So this is half-life for first order. Now, just see the expression. Just try to understand the expression and what all things this expression is telling you. If you see, my dear students, your T half is has what expressions it has? It has ln of 2, that is natural log of 2. You can also say that t half is equal to natural log of ln of 2 is 0.693. The value is this, so this is equal to this. So my dear students, your rate constant k is a constant and 0.693 is also a constant value. So can I say that the half-life of the first order reaction does not depend on the concentration of the reactant? It is a constant value. It will never change, be it any concentration of reactant. So this is the most important thing to note, my dear students. So you just write a note here that half-life of first order is independent of initial concentration of reactant. So this means that if you are ever asked to plot a graph between T half versus concentration of reactant, what will you say? The graph will always be a straight line. It will always be a straight line. It will be constant. It does not change with the initial concentration of the reactant. Unlike if we talk about the zero order, the expression for zero order was A upon 2K. That is, it actually did depend on the initial concentration of the reactant, and that is the reason your half-life was changing again and again. But if we talk about a first order reaction, and let us say you have some 50 amount of your reactant, then you the first half-life came T half and it is 25, then again half-life, let's say it is 12.5, this is again T half, and let's say it is again 6.25, my dear students, this is again T half. Let me tell you, for a first order reaction, my dear students, if this is 10 minutes, then if it was a zero order reaction, this definitely would have been 5 minutes because the concentration has changed, right? Yes, but for a first order reaction, this will also be 10 minutes and this will also be 10 minutes. That is, for a first order reaction, the half-life is independent of the initial concentration of the reactant and it will always remain the same, whatever the concentration of your reactant is. And this is something you need to understand, because in questions you will be asked again and again. They'll not tell you that the half-life of the first order is this. They'll just say that there is some order of reaction and there the half-life is constant. So you have to guess that it is only the first order reaction where the half-life is constant, right? Yes. So this is the expression which you need to understand. This was the most important part of the first order reaction, from where conceptual questions can be asked. So just write it, write the notes, write the graph. That is something very, very important. I hope you've written it. For a first order reaction, the half-life is independent of the initial concentration of the reactant. It is independent of the initial concentration of the reactant. I hope you are clear with this particular part. Okay, perfect, my dear students. Now let's try to solve a few questions and have a grip on this first order reaction. Okay, we have completed everything about it. Now we'll solve some questions. So here is the question. Try the question yourself. For a zero order reaction, plot of the curve A minus X versus time is linear with. So my dear students, how are you going to do this question? Pause the video, try the question yourself, and then you will have to see the approach. Okay, so you have curve between A minus X. So you have some curve like A minus X here, and this is time. So how are we going to understand this? See, I hope all of you remember that your initial concentration A0 is given by A and your concentration of the reactant at some T time is given by A minus X, right? So you also remember the integrated rate law. K is equal to 2.303 upon T log A0 upon A T, right? Yes. I also made you understand that the graph between log of AT is equal to log of A naught minus KT upon 2.303. Do you remember this? Do you remember this, my dear students? Yes. We know that A naught is A and AT is A minus X. So if you are drawing a plot between AT versus T and it is a straight line with a negative slope, you know that AT is equal to A minus X. So A minus X versus T will also be a straight line with a negative slope graph, right? Yes, perfect. So this is something that was asked to you. You were asked A minus X, you actually were asked AT. Okay. It is given A minus X. It is not given log of A minus X, right? Yes. So we can't use this expression because this expression gives us AT. Okay. Yes. So we need this graph. Okay. So we need, my dear students, AT is equal to A naught e raised to the power minus KT. And this would be A minus X is equal to A naught e raised to the power minus KT. So the graph between A minus X versus T would be a exponentially decreasing plot. Okay. Yes. Either the question is wrong. Let's read the options and see. Positive slope and zero intercept. So my dear students, since they are talking about slope and intercepts, so I think there need to be a correction. There need to be log of A minus X. This should be log of A minus X. Okay. So make this correction. This will be log of A minus X. If it is a log of A minus X, then it will be a straight line with a negative slope. Okay. Yes. Because slope is always in a straight line graph. Okay. And since all the options have slopes and intercepts, so definitely they are talking about a straight line graph. So there was a little correction. I wrote the question. I'm sorry. I think I missed log part. Okay. Yes. But it's fine. We revised both the graphs. That's perfectly fine. So let's see which answer is correct. We need a negative slope. So positive slope cannot be our answer. So positive slope cannot be our answer. Negative slope, and you have an intercept. See, you have an intercept. It is not zero intercept. It is a non-zero intercept. Okay. So negative slope and a non-zero intercept. So option D will be your correct answer. Okay. I hope you're clear with this, how you're going to solve these types of questions. Perfect, my dear students. Let's move forward to the next question. If you want to write it, you can write it, because there might be a chance where you will be asked this graph as well. So you need to know this also. Okay. Let's move forward to the next question. Question says that for a reaction 2A plus B gives you C plus D, the concentration of B is kept constant. Now, since it is given one single reaction, so we'll consider it as a elementary reaction. And since it is an elementary reaction, so order will be equal to molecularity. So let's say this would be equal to A raised to the power 2 and B raised to the power 1. Okay. This is initial rate. It says that the reaction concentration of B is kept constant and that of A is tripled. Now, somehow they increased the concentration of A and they in fact tripled it. What will be the new rate? That we have to tell. So definitely the rate will change. Let us say it is R dash, and this would be equal to K into A dash. New concentration raised to the power 2 into B concentration is same. So this would be 1. They said that it is tripled, right? So A dash is equal to 3 times of A. So can I incorporate it into this? Yes, ma'am. So this would be K into 3 times of A whole square into B. This would be equal to K into 3 square is 9, A 2, and this would be B 1. Can I say that 9 into K into A square and B 1? Now just check. This part which I have circled is actually equal to R, right? Yes. So can I say that R dash is actually equal to 9 times of R? Right? Yes. So the new rate is 9 times of the initial rate. It is 9 times the initial rate. So option A will be your correct answer. So option A will be your correct answer. So you are asked such types of questions. So you need to understand how you have to do the question. Just incorporate the changed concentration. Try to derive the initial expression. Bring out the numerical values in front, and then you will see that how many times the new rate has increased or decreased. I hope you're clear with this. Perfect, my dear students. Let's move forward to the next question. The next question says that K for zero order reaction is, you are given the rate constant for a zero order reaction. You have to pause the video. You have to try the question yourself. K value is given to be 2 into 10 raised to the power minus 2. If concentration of reactant after 25 seconds, so the time is given to be 25 seconds. And you are given the concentration of the reactant as 0.5 molar after 25 seconds. Initial concentration you have to tell. You know that according to zero order reaction, AT is equal to A naught minus KT. So A naught will be equal to AT plus K into T. The concentration of AT is 0.5 plus K value is 2 into 10 raised to the power minus 2 into time is 25 seconds. Let's try to solve. This is 0.5 plus 0.02 into 25. This would be equal to 0.5 plus 0.5, which is equal to 1 molar. So 1 molar, that is option D, will be your correct answer. This is how you will be solving the questions. I hope you're clear with this, my dear students. Perfect. Pause the video, write it, and then we'll move forward. Okay, I hope you've written it. Perfect, my dear students. Now, let's try one more question, and this question will be the last question for our today's lecture. But you have to pause the video and you will have to try this question yourself. What does the question say? The question says that, show that for a first order reaction, time required for 99% completion is twice for the time required for the completion of 90%. Okay, so let's try to do this question. I know that I'll have to use the integrated rate law here. So let's say the integrated rate law is K is equal to 2.303 log A naught upon A T. Okay, now I have two conditions. One is 99% completion and the other is 90% completion. Okay, so I'll just differentiate the two. Now see my dear students, if A naught is the initial concentration, this is the initial concentration, obviously A naught will be the initial concentration here as well, right? Yes, perfect. Let's say AT is the concentration at 99% completion. This will be equal to A naught initial minus 99 upon 100 of A naught. And this will be 90%. So AT here will be equal to A naught initial concentration minus 90 upon 100 of A naught. Right? This will be the value for AT. Since, my dear students, your temperature is not changing, so the rate constant will not change. Rate constant only depends on the nature of the reaction. The nature of the reaction is same, and on temperature, and the temperature is same. So in both the cases, K value will be same. The time here would be 99% and the time here would be 90%. Okay, so now let's try to put all these values in the integrated rate law for both of them. So I'll say K is equal to 2.303 upon T, 99% log A naught upon, this would be A naught upon 19, I'll have to subtract it right here. I'll have to subtract it. This would be equal to 100 A naught minus, this is A naught upon 100. This would be A naught upon 100 and this would be 10 A naught upon 100, which is actually equal to A naught upon 10. Let's keep it as 10 A naught upon 100 only. Okay. So now I have to put these values. This would be A naught upon 100. A naught upon 100. I am sorry, A naught upon 100. Yes. This is the value for AT. Yes. Similarly, I'll say K here would be equal to 2.303 upon T, 90%. And this is log A naught upon 10 A naught upon 100. Right? I hope it is clear. Now, can I cancel A naught by A naught? Can I cancel A naught by A naught? Yes. So here, K will be equal to 2.303 upon T 99% log 100. Let's write it here. K is equal to 2.303 upon T 90% log 100 upon 10. So 10 will be cancelled, right? Yes. Now this is the first equation and this is the second equation. And since, my dear students, first and second equations rate constants are exactly equal. So can I say that? Can I say that? I'll have to do something here. I have to erase this line, no? Yeah, so I'm just erasing it. Okay. Yes, perfect. So my dear students, now tell me, can I say that 1 will be actually equal to 2? Because both the rate constants are same. So let's equate both of them. 2.303 upon T 99% is equal to log 10 power 2, right? Sorry. Log 10 power 2. This will be equal to 2.303 T 90% log of 10 power 1. So 2.303 cancelled here, and log 10, can I say 2 log 10 upon T 99% is actually equal to log 10 upon T 90%, and we know that log 10 is actually equal to 1. So we'll use this into this. So can I say that 2 upon T 99% is actually equal to 1 upon T 90%. So T 90%, 2 times of T 90% is actually equal to T 99%. So were we supposed to derive this? Let's just check that the 99% time is actually equal to 2 times of 90% time. What were we supposed to calculate? You were supposed to tell that the time required for 99% completion is twice the time required for 90%, and we did derive that. So I have to write like I used to write in my exam whenever I used to prove something. Hence proved. So I did prove that with a big smile, right? Yes. So if you are using the concepts clearly, you'll definitely be able to achieve, you'll definitely be able to prove whatever is asked in your question. Okay. So yeah, this is how I did this question. I just used the integrated rate law. I used the concept that the rate constant will not change as long as the time is the temperature is same and the nature of the reaction is same, and both of them were same. So I just put the values in the two expressions, did equate them, and calculated what I needed to. Right? Yes. You can pause the video, write it, try the question yourself. Only then you will be clear with the concepts. Okay, perfect, my dear students. With this, we will end our today's session. We have completed everything about first order. Obviously, pseudo order and the nth order is yet to be covered, but the main part of first order reaction is completed. Today we have studied about the integrated rate law, the graphs related to the rate laws, half-life period, and many practice questions. Now you have to practice yourself. You will be given the practice sheet. You will have to try the questions yourself. Only then you will be able to excel in this physical chemistry part. Okay. Yes. So I hope you enjoyed today's session and you'll definitely study harder and make ma'am feel proud. We'll meet in the next lecture. Till then, keep studying. All the very best. Thank you so much.